In this short video, we will discuss features about a nucleus that makes it radioactive. And we'll broadly answer the question, why are some nuclei radioactive? Okay, not every nucleus is radioactive, so let's see what makes them radioactive. Well, probably the best place to start would be to look at the belt of stability. So if we draw some coordinates here, we can have the number of neutrons and the number of protons here, and then pretty much we'll have, and I'm simplifying this diagram, a straight line and then a slightly steeper line and then a steepest line. So maybe I can delineate these cutoffs with another color. Okay, so let's see if I can get the pen in the right place. Yeah, so I made this distinction about here. And then I made another distinction about here. Okay, so roughly speaking, if you are on this line, and this line is not as thin as I'm making it here, but if you are on this line, you are not radioactive. So there's something to do with the ratio of neutrons and protons that will either make a nucleus radioactive if you're off this line too much, or not radioactive if you're on this line. The ratio here should be about 1 to 1 for this part here. Now this is up to approximately 20 protons. This ratio here should be 1.25 to 1. Up to about 82. And then above here, we've got about 1.5 to 1. And essentially, the closer you are to this line, the less likely, and it's quantum statistics now, the less likely you are to be radioactive. So if you, let's use a blue color, if you find yourself over here, then if this is your neutron to proton ratio, you're going to decay that way. Conversely, if you find yourself over here, you're going to decay that way. And if you're on the line, you're just going to stay there. So that's pretty much one of the important features about radiation. So let's have a look. So let's have a look at an example. So we'll put e.g., let's look at carbon. So let's look at carbon 12. And if we break this down, we know we have 6 protons. We've got 12 minus 6, which is 6 neutrons. I've got 6 electrons. We'll put them there. We're not really interested in electrons here because we're looking at the nucleus. But importantly, I've got 6 protons and 6 neutrons. So my number of neutrons divided by the number of protons is 1, or rather 6. Let's make that a better 6. 6 divided by 6, which equals 1. So therefore, the neutron to proton ratio is 1 to 1. Now, should it be 1 to 1? Yes. How do we know? Well, let's click on this red pen and look at that. Look at why this should be a 1 to 1 ratio. So we can see that there are 6 protons. So that means we should be in this range here. So 6 is about here. So in this range, we're stable if we have a 1 to 1 ratio of neutron to proton. So we would conclude, therefore, that we've got evidence that the isotope carbon-12 is not radioactive. So not radioactive. And it's not radioactive because we've inspected the neutron to proton ratio, and for an atom that size, it has exactly the ratio it should have. Let's compare and contrast this with an isotope of carbon that we know is radioactive. So let's have a look at carbon-14. So let's have a look at carbon-14. Here we've got the protons. We have 6 protons. 14 minus 6, so I have 8 neutrons. I've got 6 electrons that I'll just add for completion. So if we look at the neutron to proton ratio here, the neutron to proton ratio is now 8 over 6, which is going to give me, let's get a decimal version of that. So 8 divided by 6, 1.3 recurring. So 1.3 repeated, which clearly is greater than 1 to 1, which it should be. We know it should be from previous discussions, carbon, any isotope of carbon, because remember, your location on the horizontal axis in this graph is based on your protons, not your mass. So if you've got 6 protons, you should have a ratio of neutron to proton 1 to 1 to be stable. And this is clearly greater than that. So we can see that because this is too large, we've got evidence that this isotope is neutron rich. It's got too many neutrons. If it's neutron rich, not only is it going to suggest it's radioactive, but it's going to be a negatron emitter. Negatron emitter. And you can just remember N, N. So let's recall, for the benefit of those that haven't watched the previous videos on negatron emission, let's recap briefly what we mean by negatron emission. Well, by negatron emission, we effectively want to lower the number of neutrons, right? We're neutron rich, so we want to decrease the number of neutrons. So we can take a neutron with an atomic number of 0 but a mass of 1, and this will decay into a proton with a mass of 1, an atomic number of 1, plus a beta particle, a negatron. So we're assuming a mass of 0, although that's only an assumption, because we know that beta particles do have a mass, but we're assuming it's negligible compared to the mass of the neutron and proton. It has a charge of -1, and we'll write beta for beta particle. And we have an anti-electron neutrino, which has neither a mass nor a charge. Again, the neutrino really does have a mass, but we're just assuming that it doesn't based on the way you would calculate this. Okay, so that's what we mean by negatron emission. We can go ahead and double check our baryon and lepton number. If you haven't watched the previous videos, you'll have no idea what I mean by baryon number and lepton number. But if you have, you will know exactly what I mean. So baryon number must be conserved. Let's check. And then lepton number must be conserved. Essentially, baryons are clusters of 3 quarks, so neutrons and protons are baryons. So you can't create or destroy baryons, so if I annihilated a neutron, which had a baryon number of 1, that's fine because I created a different baryon, which has a baryon number of 1. Beta particles are not baryons, so they don't have a baryon number. And electron neutrinos, or anti-electron neutrinos here, are not baryons, so they have a baryon number of 0. So 1 baryon went in, 1 baryon came out. Conservation of baryon number. Baryons are not leptons, so you can't contribute a lepton number if you are not a lepton. A negatron has a lepton, is a lepton, and has a lepton number of 1. An anti-electron neutrino is a lepton and has a lepton number of -1. No leptons went in, a sum of 0 leptons came out. So we've got conservation of baryon number and lepton number. So not only can we predict from the neutron to proton ratio that carbon-14 is radioactive, but we can also indicate the probable type of radiation exhibited. In this case, we knew it was neutron rich, hence a negatron emitter, and we can see what that would decay into. So an example of what we could see from this, if we were to take this knowledge we could say, for example, we could have, let me just get this in the right place. Try to stop my phone from ringing again. Okay, sorry, I've just silenced my phone. Somebody wouldn't leave me alone. Okay, in COVID land. Okay, so if we know that this is the case, then let's see what we could have. We could have carbon-14. It could decay. Now let's see what happens when it decays. Well, one of its neutrons is going to be replaced by a proton. It's not going to change the mass. 1 becomes 1, but it is going to change the atomic number. The atomic number is going to increase by 1. So I know that this is going to be 14. And I know that 6 is going to increase by 1 to 7. So I immediately know I've got an isotope of nitrogen, which has an atomic number of 7. And now I can just put the remaining ingredients, the beta particle or the negatron, and the anti-electron neutrino. And we can double check, recall that A Z of X must equal A Z of X prime. So we have conservation of atomic mass and conservation of atomic number. So we can double check that. So 14 equals 14 plus 0 plus 0. That's a true statement. And we have 6 equals 7 plus -1 plus 0. So we have obeyed our little guide rule here, and we are done with that sequence. Okay, so let's go back to our graph for a moment. Again, you would have to essentially know where you are in this graph, right? You have to know whether you're looking for a 1-to-1 neutron to proton ratio, or a 1.25 to 1 proton ratio, or a 1.5 to 1 proton ratio. Let's have a quick look at if we had a let's see, we've seen a negatron emitter. What about a positron emitter? Let's say we had a positron emitter. Let's get a black pen. So recall, a positron emitter would have, rather, instead of would have, would be. Would be proton rich So let's have a look at a positron emitter. Let's look at the equation for how a proton emitter might decay. So, for example, first of all, how would you know, I guess, e.g., for an element with an atomic number less than 20, let's just keep it simple. For an element with an atomic number less than 20, so something between hydrogen and calcium, then if you were proton rich, your neutron to proton ratio would be something like well, it should be 1 to 1, so it would be a number less than 1 to 1, right? So any number less than 1 to 1, that's how you would know it would be neutron deficient or proton rich. Neutron deficient or proton rich. And that's how you know it's positron emitter. Positron, proton, just like earlier we had negatron, neutron. So let's see what let's remind ourselves what that would look like. Again, this is outlined in a previous communication, but if you haven't seen that, you will be lost at sea, I guess. So let's send you a beacon of light. Well, the goal is to reduce we've got too many protons, so let's reduce them. Well, we know protons can decay into neutrons and positrons, which is just an anti-electron, and a regular electron neutrino. We can double check our baryon number and our lepton number. Baryons are collections of 3 quarks, so neutrons and protons are baryons. They obey the strong force. One baryon goes in, one baryon comes out. Electrons and neutrinos are leptons, so they are not baryons. They don't have a baryon number. So we have conservation of baryon number. Baryons are not leptons, so they don't contribute to the lepton number. So no leptons go in, no leptons should come out. Let's double check. A positron has a lepton number of -1, and an electron neutrino has a lepton number of +1. So they cancel each other out and sum to the left side, which was 0. So we have conservation of baryon number, conservation of lepton number as we needed. So everything looks okay there. Let's see what we would have if we had something that was let's see if we can find an example of let's go back to black. Okay, so we can take a look at fluorine. Fluorine's a funny example. It's a positron emitter, although it does have a 1-to-1 ratio. It opens a can of worms I really don't want to get into in this video, or at all for my students that are hopefully going to watch this video. I hope my students watch my videos. We'll never know. But there will be, you can clearly see there's a 1-to-1 ratio of protons and neutrons. There's 9 protons, there's 18 minus 9, which is 9 neutrons. So you would argue you have evidence that it's not radioactive. It is radioactive, however, because it has an odd number of protons. So there's a different rule. I don't want to get into it in this video, but it would be a go-to example of a positron emitter. So let's have a look. Let's follow this rule. See that it will be a positron emitter. Okay, so we have a proton is going to decay inside fluorine 18 to give a neutron, so the mass won't change. So I know that that number is going to be 18. But I know that the atomic number decreases by 1, so that's going to be 8. Well, if that's 8, it's got to be oxygen. And now I can write what's left. I've got my positron with its +1 charge, and I've got my electron neutrino. Again, we have to have, ironically, despite there being no such thing as conservation of mass, we use conservation of mass. One of the many ironies in science. Because it's useful, we use it if it's useful, right? Okay, the sum of the atomic masses and the atomic numbers can't change, they have to be conserved. I guess therefore you can use it. We just can't create this, well, Of course you can create or destroy mass, E equals mc squared. But despite that, this is how we use it to get the right answer at this general chemistry level. So let's double check that we've followed this idea that we conserve mass. Okay, so I know that 18 must be conserved, so I have 18 on the left, I have 18 on the right, plus 0, that looks conserved. I've got 9 on the left, so I've got 8 on the right, plus 1 is 9, plus 0 remains at 9. So I've got conservation of mass. Okay, so again, to conclude this video, which is still around 20 minutes, so it's still a reasonably short video, why are some nuclei radioactive? Neutron to proton ratio. Neutron to proton ratio means that they're radioactive. Outside of that, just in the last minute or two, anything with 83 protons or more, so all of this stuff, is radioactive. Because it's got more, or its atomic number, or its number of protons is greater than 82. So 82 seems to be the limit at which you're just too big to be stable. 82 is the limit beyond which you're just too big to be stable. So lead is the atom with atomic number 82. Bismuth has an atomic number 83. Bismuth and above are just too big to be stable. So they are always radioactive. You tend, again, just to summarize some features here, if you're neutron rich, you'd be over here, right? You've got too many neutrons. Neutron rich, you are negatron emitter. Conversely, if you're over this side of the black line, you are proton rich. So you're trying to go back that way, and you would be a positron emitter. And if you're just big and you're up here, you are much more likely to be an alpha emitter. And remember, alpha is a helium nucleus. Best way to lose mass quickly is to spew out alpha particles. They tend to be reserved for the big heavy elements. Okay, so this is just some useful things to consider when you're looking at a nucleus and you're trying to ascertain whether or not it's radioactive and predict what type of radiation it will undertake to reach stability again.